let's talk about the relationship between blood pressure, blood flow, and the resistance to blood flow. And we can sort of put this into the broader perspective. The heart simply contracts to pressurize blood. It's the pressure gradient that the heart generates that drives that blood, right? So the heart is a pump. It is pressurizing the blood, and pressure drives flow. And that's related by what we see here in Poiseuille's law, right? Poiseuille's law states that Q, which is really flow, right? It's over here, indicated by this arrow, right? So flow equals the pressure gradient divided by the resistance. And so, again, we'll get into the details of this in a minute, but big picture, right? The heart is generating pressure to drive flow. And the amount of flow that goes through a particular tissue based upon that pressure is determined by the resistance, this third variable here, right? And what we see is that while pressure and flow are directly proportional, in other words, if the pressure gradient, delta P, I'll explain that pressure gradient in a second, but if the pressure in the arteries or veins, or capillaries for that matter, goes up, then the flow will go up, right? These are both on the top of the equation, if you will, right? So delta P goes up, then Q goes up, flow goes up. Resistance, on the other hand, right, is on the bottom of this fraction, and which means that resistance and flow are inversely proportional. So let's leave pressure alone for a moment. Let's say pressure is normal. If resistance goes up, right, then flow would actually go down. That's what's known as an inverse relationship. And the way resistance goes up in blood vessels is by having them constrict. Well, that's the primary physiological way for resistance to go up, is to have blood vessels actually, the smooth muscle in their walls contract, which constricts the vessel and makes it smaller in diameter. We're going to talk about the radius, but radius and diameter, right? This measurements of the caliber, if you will, the size of the pipe, right? And so if the vessel constricts, then resistance would go up, right? A smaller pipe would have more resistance. And if resistance goes up, then flow goes down. And again, let's just go back to a simple example here before we get into the details, right? If we start to exercise, we want blood flow to our muscles to go up. Well, one way to have that happen would be to increase our delta P, right? Remember, we said those are directly, or delta P is, your blood pressure is directly proportional to flow. So we could just make our blood pressure go up by, flow to our muscles go up by doubling our blood pressure, right? You'd get a doubling of flow. Well, doubling your blood pressure is dangerous, right? We don't want our blood pressure to rise dramatically during exercise. Does it go up a little bit? Yes. Does it go up enough to increase blood flow to muscles by 4, 5, even 10 times or more? Absolutely not, right? We would have a stroke, a blood vessel would break. Okay, so we can't increase, right? So basically what we need to do is adjust flow to individual tissues by adjusting not the delta P, not the pressure, but by altering the resistance, right? So at a given blood pressure, or almost the same blood pressure during exercise, what we want to have happen at the muscles is have the resistance go down. Because again, if the resistance goes down, inversely proportional, right? Resistance goes down, that means flow would go up. And that's exactly what you want to have happen. You might remember in a previous video, I talked about how during exercise, blood flow to our GI tract often goes down, and actually maybe to a few other tissues as well. And so at those tissues, we wouldn't want resistance to go down. We want resistance to go up, right? So those tissues, the blood vessels constrict, resistance goes up, and because this goes up, flow to those tissues goes down. Again, that inversely proportional relationship. Okay, so let's examine the components within Poiseuille's law a little bit more closely. And one of the things I want to point out is that Poiseuille's law described what's called laminar flow. So look down here in the lower left, right? Laminar flow it's basically the opposite of turbulent flow. Turbulent flow is what comes out of your faucets at home, right? It's mixing and bubbling and whatever, right? It's not a smooth flowing fluid as a general rule. And well, let's say we turn your spigot on all the way, right? Maybe at low flow rates it might be more laminar, so the idea behind Poiseuille's law is it describes laminar flow, which means, and a lamina is a layer. It means that the fluid flows in these layers. Now, these are not layers that you would be able to see or discern, but what it means is these are layers of fluid that are moving at different speeds. And the reason they're moving at different speeds is because the fluid flowing against the walls of the vessel, right? At the wall of the vessel, actually at the wall of the vessel, there's fluid that's not moving at all, right? Strangely enough, right? But so the fluid right up against this blue wall blue vessel wall here would be rubbing against it, right? And that actually, despite it being a liquid flowing against the surface, that actually generates friction. And friction creates a resistance to flow. And so the fluid moving against the wall directly would be moving the slowest. And the farther you move toward the center of the vessel, the more the fluid is against other layers of fluid, first of all, and the farther you are from the source of resistance to flow at the wall. And so we have what's called a parabolic, a term down here. This shape right here is a parabola, right? This arced shape, trying to trace it, right? You have a parabolic flow profile, and that means that the fluid moves fastest in the center and slowest at the edges of the vessel. Okay, and so Poiseuille's law describes laminar flow. We can talk about turbulent flow a little bit later, maybe. All right, so we've got another vessel up here at the upper right, and I want to define the components within Poiseuille's law, right? What is determining flow? Well, delta P is the pressure gradient along the vessel. Okay, so we've picked two spots here. We've picked this location and we've picked this location to measure two pressures. Okay, and we've got our parabolic flow profile here in the center between the two, right? And the idea is that there has to be a difference in the pressures, the hydrostatic pressure, the physical pressure of the fluid on the walls of the container. There has to be a difference in pressure at P1 versus P2 for flow to occur, right? If the pressures there were the same, P1 minus P2 would equal 0, and our delta, which is delta P, right? P1 minus P2 is the difference, delta P, and it would be 0. If you have 0 delta P, go ahead, plug it in over here. What's your Q going to be? Zippo, right? So the good news is, as a fluid flows through a pipe, like our blood vessels, because of the frictional elements that I was talking about down here, our pressure falls, right? We lose energy as the fluid flows through the pipe due to the frictional forces. So P2, if our flow is going from left to right here, P2 would always be lower than P1, which means we'd have a delta P and we'd have flow, right? Now, having said that, the greater the difference between P1 and P2, the greater the flow will be, right? So, and again, what we define as this, so we can define a delta P as within a single blood vessel, within a single capillary, within your aorta. We could also do it as your entire cardiovascular circuit. We could say delta P is your blood pressure, literally, because your blood pressure coming out of the heart has a mean of, I'm going to round up here, a mean of about 100 millimeters of mercury, and the blood pressure in your atria of your heart is about 0, almost, not quite, which means your delta P is essentially 100 millimeters of mercury, almost. Right? That would be the delta P for the entire circuit, and we could use that value to help us determine what flow would be, right, if we want to talk about the whole circuit. So Poiseuille's law is very handy, right? We can talk about an individual vessel, or we could talk about the circuit as a whole. right? But again, because of our frictional forces, we're always going to have a fall in pressure as we traverse the vessels. And actually, I can trace that for you. If we were to look at the pressure in our blood vessels, and I'm going to back up. I'm going to go back to the pressure in the ventricle first. If I were to trace the pressure in the ventricle, it would look like this. It would be high and then really low, and then really high and then really low, right? Now, as I come out of the ventricle, right, we're just sort of physically shifting out of the ventricle and into the aorta, our pressure is still pulsatile, but now it's going to look like this, right, in the aorta. Because the valve is closing, right, after ejection, right, so this would be ventricular pressure. This would be the aorta. I mean, we could do pulmonary trunk too, but of course the pressures would be lower. Right? And then what's going to happen as we move out of the aorta into the smaller and smaller and smaller vessels? Well, first of all, we talked about the elastic elements, qualities of the arteries and how that dampens our pulse pressure. So the difference between the high and the low here is our pulse pressure. And the farther we move out, because of friction, it's going to do this, right? Our pulse pressure is going to get smaller and smaller, and our pressure is going to fall lower and lower. And so we get way out here. Now we're out in the arterioles. And I kind of skipped over the muscular arteries and, elastic arteries. Well, the aorta is an elastic artery. But the idea is overall, as we move out farther and farther, the pressure falls. We lose the pulse, right, component. And then we move into the capillaries where our pressure continues to fall. So here's our capillaries. And then we hit the veins, and guess what? It's going to continue to fall. I'm trying to match this up. Right? So this would be veins, where the pressure is quite low. And then guess what? All the way back around. I got to go around my label. And you're going to come back into the ventricles again to repressure, well, into the atria first, but then into the ventricles to repressurize and sort of boost the energy of that and pressure of that blood, so that it moves off forcefully into the aorta and so on. Okay? So again, delta P, you pick the spot, right? If you want to talk about pressure gradient, the delta P in the capillaries, measure between here, there's your P1, measure there for your P2. If you want to do it in your aorta, pick, your P, and again, you'd have to use a mean because of the pulsatile nature here, right? You could sort of take an average here, right? It would look like this, sort of sitting in the middle of everything, right? But your P1 would be here, and your P2 would be, at the end of the aorta, out here somewhere. And you get the idea, I hope. Again, we can pick the vessel or groups of vessels that we want to assess here in terms of their flow. Okay? All right, so we hopefully have a handle on what delta P is. What is R? Well, R is a little bit more complex than delta P. And R, resistance, equals 8L eta over pi R. Actually, I'm gonna highlight this guy a little bit. Pi R to the fourth. Right? That's the exponent to the fourth power there. All right, so let's sort of assess all these components of resistance that are, remember, resistance is opposing flow. Okay? Now, it can oppose it a little or a lot based upon how big these individual factors are. Right? So let's look at, well, let's start with the easy ones. 8 and pi are constants that are within the equation to account for the fact that we're flowing through a cylinder. Right? Again, we have to assume this cylindrical shape of our blood vessels for Poiseuille's law to be truly accurate. Okay, so we can done with those, right? They're a constant. L, I should have gone up here. L is length, right? So length, the length over which we are assessing this flow and the pressure gradient that goes with that, is going to be a factor in the resistance. And remember what I said over here in the bottom left, right? Over here about the resistance to flow being largely due to friction. Well, the longer the blood vessel segment that we want to talk about, the more length there is, obviously, right? And the more vessel wall that we're rubbing up against, and so therefore, the greater the length, the greater the friction, and the greater the resistance. Aha, we're back to directly and inversely proportional. So L and eta, this is eta, are directly proportional to resistance, while pi and r for radius are inversely proportional. Okay, so, and this is a one-to-one relationship here. If the length doubles, the resistance doubles. Here's a really good example. You have a garden hose, on a spigot outside. It's 25 feet long. Okay, you're going to have a certain amount of resistance based upon that length of hose, and again, the radius goes into that as well, but length for the moment, right? So 25-foot hose has a certain amount of resistance, right? Due to that resistance, at a given pressure, which we're going to leave constant here, you're going to get X amount of flow. What if you then take another 25-foot hose and connect it to that, right? So now you have 50 feet of hose instead of 25 feet of hose. In other words, you just doubled the length. If you doubled the length, what happened to the resistance? It doubled, right? Again, directly proportional. Plug that back over into Poiseuille's law. If the resistance doubles, then what happens to the flow? Does it double too? No, right? Remember, inversely proportional, right? So like sort of the opposite effect. So if the resistance were to double, then flow would be cut in half, right? So every time you double the length of your garden hose, the flow out the end of your hose at a given pressure would be cut in half. Okay, and again, so that's one of the key components here, right? You have to send blood flow all the way from your heart to your big toe and back. The farther away you are from the initial source of pressure generation, the heart, the more resistance you're going to have, right? So tall people would obviously have, right, their limbs are longer. They would have more resistance than people with short limbs, right? Now, that doesn't mean it's not overcome and compensated by something else, but right? But that's just the physics of it, right? The longer the vessels are, the more resistance they would present to blood flow. Okay, here is eta. And let me back up for 1 second. Remember length. So think of your coronary arteries, your coronary blood vessels, right? They leave the aorta immediately after it leaves the heart, right? As it is, like where it attaches to the left ventricle. So those coronary arteries and blood vessels are really short. Guess what? That is a component that would determine them as having relatively low resistance and therefore relatively high flow at a given pressure. Now, does that mean they have 3 times the flow as your big toe because they're closer? Not necessarily, because remember, we still have to talk about the other components of resistance here, right? It could be true, but it's not the only thing affecting, length is not the only factor affecting resistance. Okay, let's talk about eta. So eta is our symbol for viscosity. Viscosity is the, if you will, the thickness of blood, like so in physics terms, it's a measure of how much the molecules in a solution sort of stick to one another, right? And other things for that matter. Honey has high viscosity, right? It tends not to flow readily because it's sticking to itself more, right? The more interaction between the molecules of honey than there are between the molecules in water. So we do not want high viscosity blood, right? Check it out. It's on the top of the equation here. If viscosity is high, resistance is high. If resistance is high, flow would be low, right? So what's the major determinant of blood viscosity? The major determinant of blood viscosity is hematocrit. Right? We talked about hematocrit when we talked about blood and blood components, right? Hematocrit is the percent of red blood cells in whole blood. Basically, it's a measure of how many cells there are floating in your bloodstream. And the more cells there are, the more red blood cells largely that are floating in your bloodstream, the more they're sort of banging into each other and creating resistance, right? So then it's not molecules that are sticking to one another, but it's just the red blood cells bouncing off one another, as well as bouncing off the walls of the vessel. So high hematocrits are dangerous because they generate high viscosity, and high viscosity obviously would tend to diminish blood flow. People that take drugs to enhance their hematocrit for aerobic sports, aerobic events like cycling or marathon running, they have to be very careful because having higher red blood cell count is good in terms of aerobic activity, but if you push it up into a danger level where the viscosity of the blood becomes too high, they can end up with heart failure, which means the idea there is that basically the heart can't overcome that resistance and they cease to be able to push their blood around the blood vessels effectively. And it can kill you. Okay, so there's viscosity. Is viscosity variable over time? Slightly, but it's a slow process and it's all about oxygen carrying. It's not about sort of trying to regulate blood flow, right? That's controlled by, elements related to oxygen carrying. To go backwards for just a second, is the length of a vessel varied to adjust the flow? That's weird, right? You can't adjust the length of your brachial artery to determine the flow to your arm, right? That your brachial artery is your brachial artery, right? And so length is a fairly fixed component of resistance. Okay, so we got to move over here to the last one. We've got the radius. And actually I can do this. Whoop, there we go. There's the radius of the pipe in question, the blood vessel in question. And so we'll come back to this, to the fourth power here for a second, but remember, inversely proportional. So as the radius goes up, as the vessel gets larger, the resistance would go down. A fire hose has a larger radius and therefore lower resistance than a garden hose, which has a smaller radius, right? That's just logical. And again, what that means, the rationale for that, is that there's more fluid, come back down over here, there's more, in a larger pipe, there's more fluid that is farther away from the walls in a large pipe than there is in a small pipe, right? So it's less affected by that resistance, the friction at the walls. Okay, the smaller a pipe becomes, the more the percent of blood that's in contact with the vessel walls goes higher and higher, right? There's less in the middle of the pipe because the pipe's getting smaller, right? And it's a surface area to volume ratio kind of thing here, but just we can stick with the idea that a larger pipe has more fluid in the center, which is not rubbing up against the walls essentially. Okay, so now the last thing to point out and to jump up and down and scream about is this. Right? That's to the fourth power, right? Not squared, not cubed, to the fourth power. Why that's hugely important is that changes in the radius are massively more important than changes in length or viscosity on resistance, and therefore on flow. Right? Again, this to the fourth power bit makes this enormously more important as a factor affecting resistance and therefore flow. The other bit that makes it enormously important, unlike length and viscosity, which are, short term, at least relatively fixed, the radius is not, right? We talked about this previously in another video, where we have the smooth muscle in the walls of this vessel, and that smooth muscle can constrict to make the vessel smaller, or it could relax, in which case the walls would distend outward under the pressure of the blood within them, and the radius would get bigger, right? And blood vessels can change, the small resistance vessels, especially the muscular arteries and the arterioles, they can change their radius quite dramatically through constriction and dilation by greater than 50%. And again, that a 50% change in radius would be a 16-fold change in resistance, 16 times, just by changing this by 50%, right? And so, but right, if you cut it in half, if we change resistance by 16-fold, right? Guess what happens to Q, right? Again, similar degree of change there, right? So again, in terms of the factors in Poiseuille's law, right? The length is important, the viscosity is important, the radius is important. The radius is the one we really want to focus on because it's the physiologically relevant one that is utilized to adjust resistance and therefore adjust flow, right? Come back to our exercise example. Radius is what we're changing to change resistance here, which helps us shift, increase blood flow to skeletal muscle during exercise. Okay, last thing to talk about is, right, we talked about this idea of of laminar flow, right, over here. And again, most blood flow is laminar, but not all blood flow is laminar. And so we have to talk at least for a moment about the idea of turbulence. And basically, if there's turbulent flow, we would have to actually add another factor to our resistance equation here, right? So in other words, this resistance equation is written for laminar flow. If there's turbulence, you add what's called the Reynolds number. I don't even need to write it down or define it. But what we want to do is sort of understand how turbulence is an impediment to flow. So if we draw a vessel here, and we'll link it to something that's relatively common, right? So here's our vessel again. And now instead of this sort of cylindrical vessel, what I'm going to do is I'm going to put a blockage in here, right? And so this is an atherosclerotic plaque, right? This is a diseased vessel that's developing a deposit on the inside wall. And these are typically, they start out being fatty deposits, they become calcified over time. But what it's doing is sort of pushing into the inside of the vessel. So number one, it's reducing the radius at that spot. That's not good. That's going to increase resistance to blood flow, right? Remember, think about this and being your coronary arteries, right? Do you really want to increase the resistance to blood flow to your heart muscle? Not good, right? But in addition, and maybe even worse, is that now instead of this parabolic flow profile that we had over here, right? Now we've got this sort of, it's parabolic right up to here, right? Here it comes, right? And it's slower over here, right? And then as it passes here, what's going to happen is we create like an eddy, if you know what an eddy is, like in a stream, when there's a rock in a stream and the water flows around it and then kind of comes backwards, right? Flows literally upstream behind that rock. Sometimes you'll see like a leaf or something sitting in the water, spinning around and around in circles, like behind a rock that's sticking out of the water. And that's because you've generated turbulent flow. You're mixing the lamina. The flow's not even all going in the same direction anymore. Now, certainly, the pressure is going to drive a good bit of the flow downstream now, but our lamina are all mixed up, and we've introduced turbulence, which is an increase in resistance when that happens. Now you might say, okay, so only in diseased vessels do we have to really worry about turbulent flow. Well, there is turbulent flow normally in some vessels. It happens at bifurcations. In other words, when a vessel does this. So if the flow is relatively high and our vessel does this, right? And this happens a lot in our circulatory system. If the vessel splits, right, and the pressure is really high, we can end up with turbulent flow at these sites. That's called a bifurcation. The other place that it always happens is in your aorta, right? So if we go back over to here, right, and we were to assess our flow profile in the aorta, we're going to find a fair amount of turbulence. And the basis for that is velocity. The faster the blood moves, the more likely it is to become turbulent flow. Now, the good news is, so you'd think, oh boy, like the aorta, like we don't want resistance like to blood flow to our entire body. Well, you do have some because of turbulence, especially during exercise when that blood's moving, 3, 4, 5 times faster. But guess what? How big is the aorta? It's huge, right? And so that single vessel has a very high, large radius, right? And remember, if the radius is really big, then the resistance is really low. And flow can therefore, if this is really low, then Q can be very high. And hopefully you're picking up the relationships between the individual elements of resistance, so the individual elements of resistance, how they affect that overall resistance, and then you got to come back over here to Poiseuille's law and plug them in to see what happens to flow, how it would affect flow. Are there countermeasures to this when it happens? Sure, right? If your blood pressure were to fall, right, we would counteract that with physiological responses to boost that blood pressure. But what would happen in the meantime, right? Because if pressure drives flow, if your blood pressure falls, flow would fall. Not good, right? So how would we maintain blood flow to our tissues while that's happening? We would change the resistance, right, to help counteract that change in pressure to help maintain flow. Now it gets complicated because if you have low blood pressure, we try to maintain blood flow to certain tissues and then kind of give up on others, right? We need to maintain blood flow to your brain, but we may not worry so much about your skeletal muscles or your skin for a short period. Not that we could have no flow, but we preferentially are going to shunt blood to particular regions by adjusting the resistance. Okay.